Refraction Notes. Dispersion is a variation in wave speed within a medium due to the wavelength, which is represented by the color. Remember, in a vacuum or in air, all the different colors of light are traveling at the speed of light, but in a medium they slow down, such as water or glass, and each color has a different speed that it travels at. Dispersion in a prism is what causes our white light to separate into the component colors of the rainbow. Pause and copy. Let's get out your homework paper from yesterday, the dispersion page. We were given a starting angle of 80 degrees, and using Snell's law, the refracted angle inside the prism should be 41 degrees. Then we subtract that number from 60 to get the next angle 3 would be 19 degrees. Then we use Snell's law again to get 29 degrees for this last arrow to come out. Now repeat the same process using the violet color. We get slightly different answers. We start at 80 degrees. This one is 1 degree different. It comes in at 40 degrees in the prism. Then we subtract that from 60 to get 20. And then Snell's law again gives us 31. So each time that violet wave changes mediums, it bends a little bit more than the red did, and it comes out at a slightly different angle. Alright, changing the angle to 30 degrees on the red light, we start with 30, we get 19 using Snell's law, then 40 by subtracting, and Snell's law again gives us 78 on this side. For the violet color, we should get an error on your calculator because that last angle is larger than the critical angle, and we have a total internal reflection. So on this prism, the red light of the rainbow would be coming out, but the purple would not. So the violet travels slower inside the medium, and that makes it bend more. So it bends more at this first surface, and then it bends more again at the second surface. And so we're separated even farther. And each color of the rainbow separates a little bit different angle because it's going at a little bit different speed. Violet's the slowest and red is the fastest. Pause and copy. Chromatic aberration is caused by dispersion within a lens. Because the violet is bending more than the red, you can see it has a closer focus point. The red bends not as much, so it has a farther focus point. And these two different focus points is making our image slightly blurry and has a little bit of rainbow color around it. Pause and copy. This is a diagram I got in the book. They make special lenses called achromatic lenses, which are a combination of two lenses which correct that problem. A more common way of solving this problem is to put a coating on the lens, and we'll learn more about coatings in the next chapter. Dispersion also causes the rainbow to occur inside of raindrops. As the light enters a raindrop, it bends, and the violet bends more than the red, so it separates a little bit, and then when it bounces out the other side and comes out, it bends again and separates a little bit farther. And each color, again, bends more and more, so we get a separation of all the colors into the rainbow. Pause and copy. Refraction. Light bends when it changes mediums. That's the definition of what refraction is. When light slows down, it bends towards the normal. When light speeds up, it bends away from the normal. Pause and copy. When you're looking at something in water, light is coming from the object in the water. As the light ray leaves from the water to the air, it bends when it comes out to your eyes. So light is following along this path. However, we're used to seeing along straight lines. So this cat is going to see the fish along this line because we're used to seeing along a straight line. We're going to think the fish is up at this spot. Notice if actual fish is down below, the image of the fish is up above where he sees it. The same thing is true with the fish. If he's looking at the cat, he's used to seeing in a straight line, so he's going to see the cat up above when the actual cat is down below. Notice in both cases, the real object is below and the image is up above. Refraction causes some optical illusions. Sometimes when the sun or the moon are down near the horizon, we see some strange effects, like this one looks like it's on a stand, or oftentimes you'll see an extra large moon or extra large sun. Another common phenomenon caused by refraction is a mirage. In a mirage, these light rays that are coming from the object actually bend around in a circular pattern, because the air down near the ground is hotter than the air above and therefore has a higher index of refraction. So these light rays are bending. And since we're used to seeing in a straight line, we see a refraction of something up above down below. The most common mirage looks like water on the road. As you get up closer to that spot on the road, you find out that there's no water there. It's just this light from the sky is bending as it comes down here because the index of refraction of the hot air down below is larger than the index of refraction of the cold air above it. Here's some other examples. In each of these cases, it looks like there's water here and you're seeing a reflection of water. It's just refraction. These light rays are bending as they're coming through the hot air. All right, pause and copy. Lenses are defined as a transparent material that change the relative direction of the light rays. Remember when we did these diagrams last week, the one that had parallel side did not really change the direction of the light, it still came out parallel, so that's not considered to be a lens. The lens is something that alters the original path of the light ray. Pause and copy. Converging lenses focus light into a point. Diverging lenses spread light out as if it came from a point. If we follow these light rays back, they all look like they're coming from this focus point. Quick sketch of each of these. Like the mirrors, the lenses also have rules for the ray diagrams. For the converging lens, light coming in parallel to the axis goes out through the focus point. Light coming in through the focus point goes out parallel, though those are the same two rules for a converging mirror as well. The third rule is different. Light coming in through the center of the lens is not refracted. This is a quick drawing of that. Light coming in parallel goes out through the focus point. Light coming in through the focus point goes out parallel, and light going through the center is not refracted. Pause and copy. Diverging lens. Light coming in parallel to the axis goes out as if it came from the focus point. Light coming in towards the opposite focus point goes out parallel. And light going through the center of the lens is not refracted. Notice rule number 3 is the same for both lenses. On this one, here's our light ray coming in parallel, and it's going out as if it came from this focus point. This one is going towards the far focus point, but bends and comes out parallel. And the one going through the center does not bend at all. For this one, to find the image, you're going to take these 3 rays that are not converging and trace them behind the lens to see where the image is. Pause and copy. Real images. The real image forms where the light rays converge. It can be projected onto a screen, and it's always inverted. For a virtual image, the light ray extensions converge, cannot be projected onto a screen, and the virtual images are right side up. Very similar to the mirrors. So for this one, the diverging lens always has a virtual image. It's always going to be on the wrong side, and you always have to trace the dotted lines behind to find it. For the converging lens, just like the converging mirror, sometimes we get a real image on the outside of the lens. Sometimes we have a virtual image on the wrong side of the lens. The lens formulas are the same for lens and mirrors. And this condition for the diverging lens and the diverging mirror, F and DI, are also negative because they're on the wrong side of the lens.